Okay, so now I want to see one more proof by contradiction, which involves a fairly sophisticated proof by contradiction. So this is theorem 7.6, which says that square root of 2 is irrational. So a very simple statement. Irrational means not rational, right? It's another way of saying that. So I cannot write it as a fraction, right? And so when we do this by contradiction, we're going to assume that it can be written as a fraction. We're going to see that that leads to a problem. Now, for this, I want to introduce a common technique, which is we're going to prove a lemma first. So what's the lemma? If P and M are natural numbers where P is prime, then if P divides M squared, then P divides M. Okay, now this is actually more generally true than what I have here, but this is what we're going to need in the proof. So let's just prove this lemma. We're going to do this by a direct proof. And I'm going to use the fundamental theorem of arithmetic to do it, even though I think you can do this other ways. So let's do this by the fundamental theorem of arithmetic. So assume that P and M are natural numbers and P is prime. Okay, by the fundamental theorem of arithmetic, M equals, let me use Q's instead of P's only because I don't want to confuse it with the other P at the moment. Where Qi for 1 less than I less than K are all prime. Okay, good. Since P divides M squared, we know there exists an L in the natural numbers so that M squared is equal to P times L, which we can already notice is the same thing as Q1, Q2, Qk squared equals P times L, and that's the same thing as Q1 squared, Q2 squared, Qk squared is equal to P times L. All right, so now the point is that the left-hand side is completely broken down into primes, and the right-hand side includes a prime. So, and they're equal, right? So, and also L can be broken down into primes, right, if I want. So the point is that P must be equal to one of the primes on the left-hand side. To them, hence, P equals some Qi or some 1 less than I less than K. Hence, but what does that mean? Hence, P divides M as desired. Okay, so this is not the only way to prove this, but it is, I like doing it this way because it kind of shows you the idea. As soon as you have to divide this and you can break it down into all these primes, then you can see that P has to be equal to one of the primes on the left, which means that it has to divide. You can see in the textbook that there's other ways to do this, but this is good for us right now. Okay, so now we have this lemma, and you'll see this lemma is going to be used in the proof of the original theorem, which is to say that square root of 2 is irrational, right? So remember, that's what we're trying to do. I proved this lemma now, and we're going to use the lemma in the proof of the theorem. And that's always what we mean when we say lemma, is it's a true statement that on its own maybe is not that interesting, but will be used in the proof of something else. Okay, so square root of 2 is irrational. Let's look at that proof. And this proof is the one that uses contradiction. Okay, so assume, for sake of contradiction, that square root of 2 is rational. So what does that mean, right? So there exists an m and an n, which are integers, and specifically n is not 0, so that square root of 2 is equal to m divided by m. Okay, and now this next statement is going to be so crucial to what we're about to do. So moreover, we may assume that m over n is written in lowest terms, meaning that m and n share no common factors. Okay, basically, if they did share two common factors, you could just cancel it out and then, give me the new fraction that doesn't. So although you could have came up with a fraction that does have common factors in the way that you expressed it with m and n, I can always remove the common factors. And so I'm just saying I want to be in the situation where I've already removed all the common factors, right? Okay, no problem. So then, let's call this thing star. So then star is equivalent to, let me put parentheses around this, star is equivalent to n times square root of 2 is equal to m. So now by squaring both sides, we find that we get n squared times 2 is equal to m squared. See, I want to get rid of the square root so that I can stick with like integer stuff, right? And now here's where we're going to use this lemma. So by definition of divisibility, we see that, well, 2 divides m squared, and by the previous lemma that we just proved, we know that 2 divides m. So then, again, by definition of divisibility, m is equal to 2 times k for some k in the natural numbers. Okay, great. So then, so now let me call this double star. So by plugging this into double star, we find, Okay, so now we get that n squared times 2 is equal to 2k squared. That gives me n squared times 2 is equal to 2 squared k. And if I cancel one of the 2's, I get n squared is equal to 2k. Okay, but now I get another very simple observation similar to one I made before. So therefore, 2 divides n squared now. And so by the previous lemma, 2 divides n. So n is equal to, 2 times something, 2 times L for some L in the natural numbers. Okay, but now this is a problem, right? So this is now a contradiction since m is equal to 2 times k and n is equal to 2 times L share a common factor of 2. But they were supposed to be in lowest form, right? So since we assumed that m over n was in lowest terms, we have obtained a contradiction. And so what's the conclusion? That means that hence square root of 2 is irrational. And we're done with the proof. I love this proof. It's a very subtle contradiction. We assume that the fractions in lowest terms, we go through this argument and we find out that both m and n must be divisible by 2, so the fraction's not in lowest terms, right? And so it's a little bit subtle, but it's a nice example of a proof by contradiction. And so square root of 2 is irrational. There's no way, there must be no way to write it as a fraction since we get this contradiction. Now it turns out that the same proof shows that if you take the kth root of any prime p, so where k is a natural number and p is prime, that will be irrational as well. Almost exactly the same proof works here. I'll have you do that on a worksheet as an exercise. So try to follow the same proof, but using to show that the kth root of any prime is also irrational. So this proof gives us an entire infinite family, the kth root of every prime, of irrational numbers. So that's already a nice large family of irrational numbers. It turns out, though, that there's many more irrational numbers, and actually there's a way to say that the size of the set of irrational numbers is actually strictly larger than the size of rational numbers. And we'll see that later on when we talk about cardinality of sets.